So we're back about looking at the roots of complex numbers. Last lesson we looked at Demoivre's theorem and how that works in terms of calculating variables that are raised to a certain power, or cis products. We're now going to start kind of look at that as an application. And when we're looking at roots of complex numbers, we're looking at finding specific points on the complex field that when you put these together, it creates a regular polygon. Okay, so for instance, if you had something to the power of 3, you get a triangle, to the power of 4, a square, power of 8, an octagon. Okay, so on and so on. And when it comes into the form of using roots of complex numbers, they're generally written in the form of z to the power of n is equal to c, where n is equal to the number of solutions that you have, and c is the complex number that we're trying to find. So when we're working with these types of variables, we're looking at calculations where we've got z is equal to cis theta, from what we've already looked at previously. But when we're calculating the roots of complex numbers, the complex number that we're working with here is if we have z to the power of n, then this here can be rewritten as z is equal to one over n. However, before we start distributing these values in, because we're working with a complex field and finding different roots, we have to start having an initial starting point and move around a unit circle in a specific direction. So instead of having theta over here, when we looked at our cis properties, we were introduced to something that kind of looked like this. And this is where the real application of this comes into play. When we're looking at using this variable inside of this function here, this is here what we call our initial position. And this here is our smallest possible argument. And it's the smallest possible argument that repeats itself and making it equally different spread between the different points. So instead of now having theta inside here, we'll rewrite this here as to the n cis theta plus k 2 pi, I'm going to do this out of the way, 2 pi all over n, and it's written in this format here. So this is using Demoivre's theorem, where we now have our initial position in here according to what our variable is in terms of our calculations, and then we have how far we're moving between each point. And this smallest possible argument will repeat itself according to how many points we're going along. So the best way we can look at this here is if let's just write this over here, we know that this is our formula now. K function 2 pi all over n. So we now need to remember this is the formula we're using when we're working with complex number fields. Okay? So let's put this into some practice right now so you can see how the calculation itself works. So for instance, if I had z cubed is equal to 1, okay? What I know about here is I can rewrite this into a cis form. Okay? So I can rewrite this here as z cubed is now equal to my complex form here, cis theta can now be written as z is equal to, now I don't have a modulus here, so I'm just going to rewrite this here as cis theta plus k 2 pi to the power of 1/3. I've now written these values out. Now if I'm looking at cis theta and I've been equal to 1, let's have a look at the unit circle we've got over here. sys1 would be equal to this position here. And what do I know about that starting position in terms of theta? Well, I know it's going to have an angle of 0. So instead of having theta here now, what I will have instead is my initial position. I'm starting from this position on the unit circle because this here is equal to 1. So when we look through these kind of calculations here, if we go a little bit further, what we can do here is let's use our distribution rule. So we've got cis, I don't have a value here, 0, I can put 0 over 3, and I'll do that here, plus k 2 pi over 3. And that's using Demoivre's theorem. And we could simplify this a little bit further because 0 over 3 is going to give me 0, so I can erase this and then just rewrite it as cis 2k or k 2 pi on 3. And this here is my smallest possible argument now. The smallest possible argument, so starting from here, I'm going to move 2 pi on 3 for every position along. Now, when it comes to working out how many points I'm going to have, that's going to relate to the variable I have up here. So I'm going to have 3 different points on my argument, our Cartesian plane over here. But what we need to remember is we need to choose values for k that will make sense. And our k values that we choose are usually the number of solutions subtract by 1. So in this example here, if I had z to the power of 3, I would use k equals 0, k equals 1, and k is equal to 2. 0 being the initial position, which is this, 1 being a movement of 2 pi on 3, and 2, another movement of 2 pi on 3. So in this case here, I'm going to replace the k with 0, I'm going to replace the k of 1, I'm going to replace the k of 2, and get my coordinate points that sit on that unit circle. So if we look at this type of question that we've got right above us here, we can say, well, when k is equal to 0, I'm going to replace 0 into here. So I'll get cis, well, that's just going to give me 0. And I know that cis 0 is equal to our starting point, which is just here. So I'm going to call that Z1. That's my first complex point here. I then have a look at my next value, which will be when k is equal to 1. I'm replacing the k with 1 now, so I have cis 2 pi on 3, which then means I know that I'm coming up on my unit circle, 2 pi on 3 is in this quadrant here. So I might say, I don't know, let's say around there, it's probably a little bit further around, but I need to find the exact coordinates. So remembering this here can be rewritten as cosine 2 pi on 3 plus I sine 2 pi on 3. Which, if we look at the coordinates of it, if it's pi on 3 here, what is x on this side? It's negative, so it's going to be 1 on 2 and root 3 on 2 pi. So they're my coordinates for my first set of data here. So this here I'll call Z2. And notice that the distance between here and here is 2 pi on 3. We now look at the third one, which is k is equal to 2. So we work out our results down here. So in this case here, it will become cis 2 times 2 pi on 3, which is the same as cis 4 pi on 3. And now we have a bit of an issue. When we work with arguments, remember the range of the argument is negative pi to pi. So that means I've got my argument range in search of that calculation or domain, sorry. So that means that this variable, cis 4 pi on 3, is outside my range. So what we need to do now is, instead of having k equals 2, I'm going to go backwards and go k is equal to -1. So therefore, I'll know I have k equals -1. And it's exactly the same kind of value that what I had up here. So I would have cis -1 times 2 pi on 3, which is then the same as cis -2 pi on 3. And again, we're coming down this time, and we're going to be coming across to this point. So this here would give me an argument 2 pi on 3, and this also would be an argument of 2 pi on 3. So if we wanted to check that, what we could do here is, if we times this by 2, which the k is doing me, it gives me another 2 pi on 3 from here down to here. But because of the argument of our domain of our argument, we actually can't go to the 4 pi, we go to the negative. And we now know that this here should be -1/2 and -√3 on 2i. So when we're looking at these different types of calculations with roots of complex numbers, we're looking at, one, how many solutions there are. And if we looked at this, if we stop a second back, we can see that this here gives us a triangular shape. Okay, an equilateral triangle shape. Okay, so we're looking at how many solutions there are. What we use as our k values is always going to be this solution minus 1. So therefore, if this was 5, you would use 0, 1, 2, 3, and then 4. Again, if it goes outside the range, you might have to come back to maybe do -2, -1, 0, 1, and then 2. Okay? Keep that in mind when it comes to your range. You shouldn't be able to come back onto the same point again as part of your roots. If you do, you've done something wrong. Okay? I have three points that lay on that circle. Now let's have a look at something that looks a little bit different. What if I had something that looked like this? Z is equal to -8i. Now if I've got -8i there, what I've got now is I've got a modulus. Now we don't keep the negative in there because the negative is just telling me where it sits on this unit circle here, or on this Cartesian plane. So if we looked at this in terms of the placement, I have -8i. So that means I'm going to be starting down here. And then, I'm not going to go through the whole process again, but just showing you a different method of this. So this will be your starting point. So if we think of your starting point, and just say that was to the power of 4. Just say if it was to the power of 4. What you would rewrite this here is, you would say Z4 is equal to cis, but this time I have a modulus. I'm not writing negative, because remember the modulus is always a positive value. So you're not going to write negative here, you're going to keep it as a positive value. The negative just telling me, am I in the negative part of the Cartesian plane or the positive part? Okay, this is always going to be positive. Remember the modulus here. Cis, now what is -i? Well, -i is the same as -pi on 2. So there's my initial argument. It's different to what we had before when it was equal to 1. So therefore we would write here -2 pi times, right there, plus k 2 pi, and there's my calculation there. If we carry this through a little bit further, what we would have is, we would have 8 cis pi on 2 negative plus k 2 pi, all to the power of 1 on 4. Okay? And then your answer here then will become this to the power of 1 on 4 cis, or let's put this 1 on 3. We'll put 1 on 3, just so you can see the calculations. Okay? 1 on 3, so therefore you will get negative 3 3 pi on 2. No, sorry. Negative 6, sorry, because we timed the bottom, plus k 2 pi on 3. And this here would be your starting argument. So now we start at negative pi on 6. So we're not starting here anymore, we're starting from here. Okay, so our initial argument was originally negative pi on 2, but once I put in my roots, it then moves its position across. And then we just carry through the normal process like we did last time. K equals 0, k equals 1, k equals 2. This here becomes 2 as your final answer, and then we carry through the calculations. So the variable up here is going to dictate what your position is going to be here, but your final initial position is when you distribute using Demoivre's theorem to get where your initial starting point is. And in this case here, we're going to be separated by 2 pi on 3 each time. This is going to change. If this was 5, it would be 2 pi on 5 between each points. Okay? If it was 7, 2 pi on 7 between each points. Okay? So you can see that as you increase your points, the distance between your different points should decrease so you can fit all of them on there. That's the roots of complex numbers. It is a little bit tricky to get your head around, but it is straightforward. It's a nice application of Demoivre's theorem. Good luck.